This conference will now be recorded.
Hello, everyone. Welcome to the ASCE meeting. My name is actually Russ Nygaard. I'm logged in as Bradley Waldrop because he normally hosts all of these meetings electronically, but he's with an uncle in the hospital right now trying to help with family. So sends his apologies for not being able to be here. Wanted to go ahead and thank you to everyone that actually joined early. It was nice being able just to chat and talk with folks ahead of time. Always wonderful when we have that opportunity during these strange times that we're living through. So at this point, let me turn the meeting over to our president, Ron Lutzenheiser, to kick us off and walk us through to our presenter. Ron, it's all you.
Thanks, Russ. Appreciate it. I wanted to make sure everybody was aware that this meeting is being recorded. We will be hosting a copy of this presentation later on our ASCE Capital Branch website for everybody to view at their leisure if they're unable to watch it today. Again, my name is Ron Lutzenheiser. I am the current president of the ASCE Capital Branch here in Sacramento. I'm a geotechnical engineer with Geocon as well. I want to thank everybody for attending our meeting this month. While we all want to get back to in-person meetings as quickly as possible, for obvious reasons, we are going to continue holding our lunch meetings virtually for the foreseeable future. But we are very happy that you decided to join us for today's presentation. I have a couple of quick announcements to make. The first is that the ASCE Capital Branch and the section officer elections will be taking place shortly. I note that at the branch level, we still have one position unfilled. So if anybody feels like volunteering to help out the branch and keep it moving forward, this would be a great opportunity. If you have any questions about joining the branch as a board member, you can go ahead and contact Bradley Waldrop or myself if you have any questions. Also, we would like to invite you to register for the virtual California Infrastructure Symposium and the Region 9 Awards Recognition Program that will be taking place at the end of September. You can nominate somebody online at the ASCE Region 9 Awards website, or you can contact Megan Leroy for more information. There should also be a link on the Capital Branch website for more information. Now, on to our presentation. Dr. Barbato is a professor in the Department of Civil and Environmental Engineering at UC Davis. He received his PhD in structural engineering in 2007 at UC San Diego. He is a licensed PE and active in the development of performance-based methodologies in earthquake, wind, and hurricane engineering, as well as in multi-hazard applications. He is the author of more than 200 technical publications. He recently received the 2020 Walter L. Huber Civil Engineering Research Prize, among many other awards. Dr. Barbato is chair of the ASCE EMI Dynamics Committee and of the ASCE SEI Multi-Hazard Mitigation Committee, the vice chair of the ASCE SEI Performance-Based Design of Structures Committee, and an associate member of the ASCE 7-22 Wind Loads Committee. So it sounds like he knows what he's doing. The presentation will illustrate the novel probabilistic performance-based hurricane engineering framework that is based on the Total Probability Theorem. This presentation will highlight the relation between this newly proposed framework and other single hazard frameworks, and will demonstrate how it can be used for the loss analysis of single-family housing in the U.S. Gulf Coast through a cost-benefit comparison of different hazard mitigation techniques and the loss analysis of tall buildings subject to both hurricane and non-hurricane winds. Whew. Okay, after all that, I'm going to turn it over to Dr. Barbato to start his presentation. Thank you.
Thank you very much. Thank you, Ron, for the nice introduction. Thank you, everybody, for being here and for inviting me to give this presentation. I will present some of my work on performance-based hurricane engineering and a couple of applications. I'll start with just a very brief introduction and background on why we are doing this, and then describe briefly the performance-based hurricane engineering framework in its mathematical form and in possible implementations, and give two examples, the comparison of the performance of different storm mitigation techniques for single-family housing, and also for the loss analysis of tall buildings, with some conclusion from the material presented. Just to give an idea of what we are talking about, I'm sure that everybody is familiar with hurricanes, typhoons, cyclones. These are all different names for the same physical object. These are storms that form over tropical ocean. They are very wide storms, and they have very high sustained wind speeds. To be defined an hurricane, they need to have a sustained wind speed of more than 74 miles per hour. They are typically common on the Gulf Coast and the Atlantic coast of the United States and on the East Coast of Asia. But with the climate change, they actually became possible, and they're happening even in Europe. We had an example in 2013 with the cyclone Cleopatra, which produces enormous devastation on the island of Sardinia in Italy. Just a little bit more of background. We need, in order for hurricanes to form, we need to have warm ocean waters with the temperature that is at least of 78 Fahrenheit. They need to be at least 5 degrees north or south of the equator. There has to be low vertical shear, wind shear, and a lot of moisture. And that is because the moisture is what produces the fuel for the hurricane in order to gain strength. There has to be also some initial disturbance and instability in order for the wind and the moisture to get enough structure to start rotating and producing what we know as an hurricane. In terms of classification, the hurricanes are generally classified using the Saffir-Simpson hurricane scale, which divides hurricanes into 5 different categories based on the maximum sustained wind speeds. Categories going from 1 to 5, from lower strength to higher strength. One of the known limitations of this classification is that it's based only on wind, but a lot of the damage and the danger coming from hurricanes actually is due to the storm surge and the storm surge rate that can produce flooding. So what are the effects of hurricanes on buildings and structures? There are several ways in which the hurricanes are acting on structures. Obviously, we have the strong winds that are producing strong pressures on walls and roofs of buildings. This pressure produces forces, moments, and can produce structural damage or also non-structural damage on the envelope. Then there is the damage produced by windborne debris and their impact on the structures. Obviously, there is penetration of windows, doors, garage doors, but the other effect that is important for windborne debris is that once the envelope of the structure is breached, we are changing the pressure distribution inside the building, and that changes completely the load path of the forces on the structure. And if the structure was not designed for this new load path, obviously we have failures. Like in this picture, you can see that there was breaching of all of this glazing from the windborne debris, but then that produces the roof to blow up due to the change in internal pressures. The other very dangerous component of hurricanes is the storm surge, which can produce flooding. And usually flooding is the issue that is most dangerous in terms of life losses, because if someone didn't evacuate and is having flooding in the streets, then they are literally stuck in the house which obviously makes it extremely dangerous for their survival. And finally, we have rain, which per se is not really dangerous in terms of life losses, but is one of the major sources of losses in terms of content and the interior of the buildings. And once you have water inside your house, pretty much you are obliged to tear it down and rebuild it from scratch. So in order to assess the performance of a structure, we really need to consider these 4 different hazards that are interacting. On the other side, we also have quite abundant knowledge in terms of approaches for performance-based engineering. Obviously, the performance-based earthquake engineering is the most well-known and the first performance-based approach that was developed for structural design and assessment. But then also performance-based blast engineering, performance-based wind engineering, and performance-based fire engineering were developed with similar characteristics. And performance-based fire engineering and wind engineering are now also accepted in our design codes and ASCE 7. In fact, very recently, less than 2 years ago, we had the first pre-standard document for performance-based wind engineering, and this document goes through the different methods of analysis that can be used to apply performance-based wind design, the definition of R modification factors and how to use it, when to use it. This document will be actually called directly in the ASCE 722 version of the code for load calculation on structural and building and non-building structures. So there is a lot of interest in having a methodology for performance-based wind design and performance-based hurricane design. And that's really the motivation and the objective of my research in this field. We know that hurricanes produce significant economic and societal losses. On the other side, we know that performance-based engineering has been very successful as a rational approach for the assessment and design of structures subjected to different types of hazards. So the idea is put them together and develop these performance-based hurricane engineering framework, which it also allows us to include other effects like the effects of climate change when the hurricane actions are expected to intensify in the next 30 to 50 years. And we need to have a methodology to actually evaluate, assess, and measure what that would imply in terms of losses on our built environment. The methodology for performance-based hurricane engineering is based or inspired, I should say, on the Pacific Earthquake Research Center performance-based earthquake engineering framework that I'm showing here in its mathematical forms. And this approach is really an application of the total probability theorem, a divide and conquer approach in which the difficult task of making a design based on the performance of the structure is broken down into simpler and independent steps, hazard analysis, structural analysis, damage analysis, and loss analysis that are able to incorporate the effect of the uncertainties in each of the different steps, and also allow different expertise to be used in different part of the analysis and design. So what are the differences then between the proposed performance-based hurricane engineering and the existing performance-based earthquake engineering methodology? The commonality is that they are both based on the total probability theorem. So we still want to break down a difficult problem in more tractable, smaller problems. However, hurricanes are by their nature multi-hazard scenarios. As we have seen before, you need to include the effect of wind, windborne debris, storm surge, and rain, and they have different ways of interacting one with the other. Also, we want to have a methodology that is consistent with the already existing performance-based wind engineering framework. It should be actually a generalization because wind is one of the hazards within a hurricane. And we need to be able to include these different hazards that are interacting. For the specific case of hurricanes, we have synchronous hazards. They are happening at the same time. And we have cascading hazards or hazard chains where the damage produced by one of the hazards can change the risk associated with one of the other hazards. So we need to have something that is able to model this in order to really consider the effect of hurricanes. The mathematical formulation is maybe a little bit scary because mathematically is a quintuple integral of all of these functions. But if we break it down into their component, we see that it's really very similar to the performance-based earthquake engineering methodology that already exists, in that we have structural analysis, damage analysis, and loss analysis that bring us to making design decisions. The differences are in the first part of the methodology, the hazard analysis, where obviously we have to consider this interaction among the different hazards. And then we have two different steps that were not in the original performance-based earthquake engineering methodology, that are the structural characterization and the interaction analysis. These are typical of wind engineering analysis of structures. The structural parameters identified during the structural characterization are those mechanical parameters or representing the characteristic of the structure that have an effect on the loading that the structure is seeing. So things like natural period, pressure coefficients, shape of the building, these are all parameters that change the load applied on the buildings when you have the same characteristics for the wind. And the interaction analysis is the step where everything is wrapped up and the characteristic of the hazard that are typical of the site and independent on the structure are put together with the structural parameters that represent the characteristic of the structure to know what are the loads that are really applied on the structure. There is also this additional curve called the chain effects that allows us to update the characteristic of the structure after we have performed the damage analysis in order to change its structural characterization. And in practice, this allows us to change the pressure coefficients applied internally to a structure once you have a breach of the envelope through a rupture of glazing or through damage in the roof of the buildings. And so that's really the mathematical formulation of the methodology that then needs to be implemented. And for the examples that I'm presenting in this presentation, the implementation is a multi-layer Monte Carlo simulation, which is a combination of stochastic simulation to implement the variability of the different parameters, followed by analysis steps where deterministic models like windborne debris, trajectory analysis, or finite element models of the structures are used to propagate the uncertainty from one step to the next. So given this general formulation, I want to now show how it is applied in practical usage for structural design. And the first example is the performance-based comparison of different storm mitigation techniques for residential buildings, and to be more precise, to single-family houses. So the case study that I'm considering is this little house here, identified by this red circle. It is an actual gable roof structures with the shingle as a cover for the roof, located in Pinellas County, Florida. Within this real residential development of houses that are pretty much very similar one with the other. We have made some assumptions on the value of the base structures and of its content in order to represent everything in dollars in something that can be easily presented to an owner to indicate what is a good idea in terms of what we should do to improve the performance of a house. This is the simplified geometric description of the benchmark structure. To make our analysis a little bit simpler, we removed from the house the garage, but the rest of the house is really this nice rectangular shape with the different windows and doors. And then we go through our methodology. We start with the intensity measure for this residential unit. The distance from water bodies was sufficient to eliminate practically any risk of flooding. So we are really focusing on the damage produced by wind and windborne debris. And our intensity measure are obviously the wind speed at the location. We need to describe the risk related to the windborne debris. We took all of these values from literature information available for the type of construction that we were considering. And then we have our structural characterization that is really describing the pressure coefficients for the given structure. And then we need to understand the variability, the real variability of these parameters depending on the direction of the wind and on the location on the roof and on the different sides of the building. And then we have our interaction analysis where we are calculating the loads that are applied on the structure. From the side of windborne debris, we are calculating the linear momentum impact of windborne debris and the kinetic energy at impact of windborne debris. The first parameters is what controls the performance of glazing windows and doors that are brittle in nature. The second parameter is what controls the behavior of steel or aluminum protection storm panels. We have also our calculation of the wind pressures on all of the surfaces of the building. You will probably recognize the C7 equation for the calculation of the wind pressure. The only difference between this equation and the C7 equation is that all of these parameters are really random variables. So they are described by distribution and not by a single design value. And once we have determined and characterized probabilistically the loading on the structure, we also need to characterize the strength of the different components on the structure, go through all of the different failure modes, pull off of the roof cover, of the roof sheeting, and all of that. Again, these are data that are taken from the literature, sometimes obtained from direct testing of the components. Some other times obtained from data of insurance claims, and then back engineered in order to obtain the numerical values. And finally, our result is this annual probability of exceedance curve that is representing the probability that a certain level of damage is outcrossed in any given year for our building. This analysis was done with 100,000 simulations. With the approach that we developed, this is actually something that can be done quite quickly. Is a little bit less than 10 minutes on a normal personal computer, and it gives you a lot of information on what is happening on the building. We broke down the losses produced by the different hazards, the breeze produced by hurricane wind speed, wind produced by non-hurricane wind speed, wind produced by hurricane wind speed, and I'm not reporting the breeze for non-hurricane wind speed because the losses were identically equal to zero. The non-hurricane wind speed is not strong enough to produce a large and energetic debris. And then there is this black line that indicates the effect of all hazards together. And the area below each of these curves provides an expected annual loss due to wind and windborne debris effects. And if you actually make the calculation, you see that when you consider the hazard independently, you have an expected loss that is a little bit less than $1,100 per year. But when you actually include the interaction among the different hazards, that's a little bit higher, is about 20% higher. And so you really need to include the interaction among the different hazards. You cannot just analyze them independently and then sum up their effects. Now, we need to go to the retrofit. This is our base structures without any retrofit. We considered 4 different strategies for retrofit or redesign. The addition of aluminum hurricane protection panels, changing the shingles, the asphalt shingles with the clay ties as a roof cover, and then considering 3 different roof sheeting nailing patterns of increasing the strength, and then substituting completely the walls and the structure from a wooden light frame structure to a masonry structure. For all of these different strategies, we considered also their interaction and combination, giving a total of 24 different design and retrofit schemes. And for each of those, again, we had to evaluate the characteristic and the variability of the strength. We used all of this information within a cost-benefit analysis procedure. We really calculated the benefit obtained by producing this retrofitted structure with a value that is discounted over a 30 years life cycle for the design life time for the structure. And we subtracted from those benefits the initial cost, the initial investment needed to obtain that reduction in losses. And this gives us an actual tool to decide what to do with the house. These are the 24 different scenarios that we have considered. And if you look at them, so the first case is our baseline house. And then we have the application of different nailing pattern for the roof sheeting, then the application of tiles instead of the different of the shingles, the application of stone panels, and then when we put everything together for the structure. The black histograms are the results for the wood analysis, for the wood structure analysis, and the blue ones are the one for the masonry structure analysis. The one that are above the line corresponds to actual savings. So when the initial investment produces a benefit that is higher than the cost of implementing our retrofit, and the one that are below the zero line obviously are where the cost is higher than the benefit. So you find probably something that you were expecting, that is increasing the strength of the roof is very beneficial, and adding storm panels on all of your windows is also very beneficial. The cost of the tiles is usually not justified only by considering the cost-benefit analysis. So if you like tiles instead of shingles, it's not an economic decision, it's more an architectural decision. And for this specific house, in that specific location, you have that also using a masonry construction is not justified only from a purely economical consideration. And obviously, these changes from house to house and from location to location, but it gives you a very clear snapshot of what you can indicate to the owner in terms of how to improve their house in a way that makes sense from an economic point of view. So I'm going now with my second application that is for structures where the more detailed analysis is granted. And we are talking about tall buildings for which, again, we need to go through the entire procedure. In this case, we have to do it a little bit more carefully because we want to be able to model with finite elements our structure in detail. These are structures that usually are connected with pretty high values and costs. And so here there is a description of the hurricane wind field with an average wind speed acting in the along wind direction, plus the turbulence that is acting in the three different directions. We can represent the variability of the turbulence using a frequency domain representation with auto spectra and cross spectra. Not going to enter into the mathematics of all of these. These are known spectra that are taken from the literature and are representing the characteristic of the wind speed across and along wind in the across and along wind direction for our building. And then we need to make our structural characterization. We are interested in three sets of parameters: geometrical properties, which if the building already exists or if you are designing the buildings, usually are characterized by a small variability. In my analysis, I'm actually considering the geometric properties as deterministic because the final results is not really influenced by their small variability. And then we have mathematical properties like natural period and damping ratio for the different natural periods, for the different frequencies of vibration. And this is done by using direct vibration measures if the building is already existing, or it can be estimated using a finite element model of the building. And then the intensity of the wind effects, which are also random, and like internal and external pressure coefficients and gust effect factors, which for the specific application that I'm presenting here were obtained directly from wind tunnel tests. So all of these allows us to describe the forces that are applied at the different floors of the building. and they depend obviously on the direction between the building and the geometry of the between the wind's direction and the geometry of the building. From these forces, we can obtain the forces along and across wind in the along and across wind direction. In the across wind direction, we need to include the effect of vortex shedding, which is prevalent near the natural period of the structure. We also include the effect of wind pressure on cladding, since a lot of the damage on these buildings can be produced by the failure of glazing and cladding. And again, we use the same equation we used before from AC7, with a slight difference, that is the wind speed used for the entire structure is over a different averaging time than the wind speed used for the cladding, just because of how the wind pressure is averaged over larger or smaller surfaces. So in the cladding, you have higher wind speeds because of the more localized characterization of the pressure on the cladding. We do our structural analysis. Here I'm reporting the results from the linear elastic structural analysis, where we obtained the interstory drift in the long wind and the crosswind direction, and the floor acceleration also in the long wind and the crosswind directions for all of the 74 stories of our building. We transform them into peak interstory drifts and peak floor acceleration using a peak factor with some assumptions. We are using the Davenport equation that assumes the process to be stationary and Gaussian, and the process is not rigorously stationary and Gaussian, but this is a simplifying and reasonable approximation for our problem. And then we need to go from the response of the building to the damage and the loss analysis. And we have considered a story-by-story approach with 4 different types of limit states for structural drift-sensitive components. These are really the structural damage produced by excessive wind. Then non-structural drift-sensitive components like partitions, cladding, this kind of things. Non-structural acceleration-sensitive components, we are talking about really the content of the building. And then pressure-sensitive cladding, as well as serviceability losses due to excessive vibration and discomfort of the occupants. The specific case study that we are considering is a 74-story building with a total value of 329 millions, located in Miami, Florida. This is our linear elastic model for the structure with its core, a central core, and then bracing system that connect with the external perimeter of a 3D frame. We went through the analysis in details of the characteristic of the wind speed at the location by tracking all of the hurricanes that passed through Miami, and finding the distribution of the wind speed, conditional to hurricane and conditional to non-hurricane, and then we combined them. We analyzed the structure, characterized it, finding all of the mode of vibrations in both directions. The structure is symmetric, so these are the results all in one direction. And then with the interaction analysis, we evaluated the power spectral density function for the loads applied at all of the different floors of the structure in the along wind and across wind directions. From that, we obtained the response in terms of displacements in the 2 directions and accelerations in the 2 directions. And then we plotted the results of our Monte Carlo simulations in terms of maximum recorded displacement at each floor and maximum recorded acceleration at each floor. These are the results for the roof of this 74-story building, where we found that actually the building is quite stiff because the maximum displacement recorded with a return period of 1,000 years is a little bit less than 1 meter in the long wind direction, where there is a big component of the average wind pressure produced by the wind in that direction. As expected, the crosswind direction that is produced only by the turbulence is much smaller. However, in terms of acceleration, we get exactly the opposite. We have that our building that is so stiff in order to remain elastic, mainly during any type of wind loading, has a lot of vibration, particularly in the crosswind direction, with a strong effect of vortex shedding. We know that this is producing a little bit of a problem because the acceleration, the maximum acceleration on the roof with a return period of 10 years is 22 milli-G, which is usually is a little bit beyond the typical limit of 20 milli-G that is considered acceptable for that level of wind speed. And also you can see that in the crosswind direction we have with the return period of 1,000 years very severe acceleration, more than 1 meters per second square. So then we apply this through the damage analysis. We have our fragility curves similar to what we would have in earthquake engineering for our structural components that are drift sensitive, for the non-structural drift sensitive components, for the non-structural acceleration sensitive components, and then for the comfort of the occupants. And we obtain a similar results to the one that we obtained before in terms of annual probability of exceedance of a given value of the loss. But we can see that actually in this case, the structural damage is almost negligible. These are the green lines shown here, structural drift sensitive and non-structural drift sensitive. This makes sense because it is designed according to AC7 and to AISC guidelines, which require the building to remain elastic under most expected wind loads. However, on the other side, you get a structure that is so stiff that the total loss produced mainly by serviceability and damage to non-structural acceleration sensitive components is really driving the losses. And I'm not going to present the results for this building, but obviously we also considered the usage of different damping systems applied to the building in order to bring down the losses, expected losses, and have a better performance for the building. But these are the type of information that can be used to improve our design, also this type of structures. I'm going to conclude because I think I'm already a couple of minutes beyond my allotted time. So we have described a performance-based hurricane engineering framework based on the total probability theorem and on methodologies that are already existing for other civil engineering subfields. But we have extended this methodology to situations that are including not only hurricane hazards, but mainly the fact that you can consider multiple hazards acting at the same time. And then there are the two applications of performance of different storm mitigation techniques and design alternatives for single family houses, and also loss assessment of tall buildings for improvement of the design. The main information is that this proposed framework can be used for important structures like that tall building directly for performance-based design, but is also very useful for calibrating design codes so that improved design can be done without having to go through all of the math and all of the methodology that I have presented here. And so with this, I'd like really to acknowledge all of the funding agencies that allowed me to do this research. And thank you very much for your attention. And I'll be very glad to respond to any question you may have. And you have also my contact information here if you have any question later on. Thank you.
I'll start out. Actually, thank you very much, Mike. It's very, very interesting. I'm familiar with the earthquake probabilistic. So seeing how you correlated that actually was very helpful for me. I can see why and similarities between the two, but seeing that you actually deal with a lot when it comes to the hurricane side of things. Very much liked the single family home also, to see that you had looked all the way down to that level of benefit, like you said, for codes. Just want to verify for myself that the cost benefit analysis, which I think is very important because it actually starts to show the reasons for doing some of these things, was the reason that there was no positive benefit for the masonry structures, just the cost of the initial build of masonry is that much more than the wood, that it just didn't benefit it, it didn't cross that line?
Yes, yeah, that's exactly correct. So and again, this is something that depends on the specific location. The house was located in Pinellas County, but if you move it on the Miami side of Florida, that consideration changes a little. The initial cost of constructing using masonry was higher than the savings that you could expect reasonably for that house in that specific location.
Okay.
Now, there are two things that are working there. One is if you have higher wind loads, then the savings coming from masonry are going to increase. And also, if you start building more masonry, the cost of building in masonry goes down. So it really depends on where you are and how expensive is to build in masonry in the specific location.
Okay, very good. Yeah, and I like the fact that, as you mentioned, depending on where you go, then your methodology would actually help you know whether or not that's a plus or a minus.
Yep.
I appreciate that. And by the way, I love your slide too that showed all the different hurricane tracks running through Miami. That was impressive.
Yeah, they do not have a good time there in terms of hurricanes. That I can. I see there is a question from Lee in the chat. I guess I'll read it and try to respond.
Please,
so,
thank you.
How can this be tied into asset management to decide which project to work on with limited resources for a community? Thank you, Lee, for the question. That's a very interesting question. I'm actually working with a colleague from Florida International University on combining performance-based hurricane engineering with catastrophe analysis, which gives a framework on how to extend what here is done for the single structure to the effect in terms of community, and to give guidance, for example, on how to change the local codes in order to have the best benefit. So you need to tie two different things here. The methodology that I'm presenting is the one that is used for design of a single structure. But then if you want to have an analysis at the community level, you need to have a catalog of all of the different structures, develop the fragility curves from all of the different types of structures, and then evaluate using the techniques of catastrophe modeling what is the benefit of doing something in terms of asset management. In that case, also the other important element is that you are doing an averaging over all of the small buildings and houses, but you also need to do a more detailed analysis for structures that are particularly important. And so if you're, for example, thinking about the transportation network in California, it's the difference of having a quick and dirty methodology to assess the several thousand normal bridges that are over the entire territory, but then for some very important lifeline bridges, you need to have something that is more accurate. And so that's how we are trying to tying in this methodology with the asset management and have a way of categorizing what best approach would give the most return on investment depending on the type of structures, the importance of the structure, and the relation of the structure with the economic development and the recovery of a region after a natural disaster. And I hope this responds to your question. So if you have a follow-up, let me know.
Thank you. Yeah, just maybe keep us informed on your research. That's would be very helpful. Thank you.
Oh, sure, I'll do. Thank you.
Are there any more questions? There was one other in the chat, but I took care of that. It was just having to do with where the presentation would be available. Just so everyone knows, the presentations we do post on our website. So if anyone wants to be able to go back and view if they missed anything or want to take a second look, it will be available.
Okay. Well, thank you very much, Dr. Bobato, and Russ, thank you for moderating this. Really appreciate your help with that as well. Dr. Bobato, we want to thank you for presenting today. We will be sending you a small token of appreciation in honor of your presentation today. Thank you.
Thank you, really appreciate it. And again, if anybody has questions, this is my contact information, and I'll be very happy to respond to any question. And thank you again for having me here. Hopefully, I'll be able to come back in future years to present also my current research on wildfires.
Oh, that sounds fascinating, especially what we're going through now. So, okay, well, thank you again. Again, we really appreciate you taking the time to present today. That concludes our meeting for today. Our next meeting will be on September 22nd, where we will be discussing development on landfills. And this will also be an online meeting. So our meeting is adjourned, and we'll be sending out a email with an online survey. Please watch for that and take the time to respond if you can, as we appreciate your input on our meetings. Thank you.
Thank you, everybody. Have a good one.
Thank you, Mike. Thank you, everyone. I will leave the meeting open. If anybody has any other questions or any comments, please feel free for another 5 minutes or so. So whatever anyone needs.
Bye.